Before we talk about how to split data, we need to understand why a particular way of splitting works. And that comes down to a fundamental assumption in statistics, the IID observation we could make. The IID assumption. IID stands for independent and identically distributed. What you're seeing here is a population of 200 data points. Think of this as the entire universe of possible observations we could make. Let's visualize the distribution of this population. Watch as these points arrange themselves into a histogram, a probability distribution. This curve represents P of X, the population distribution. It tells us how likely we are to observe any particular value. In this case, it's roughly Gaussian or bell-shaped. Most observations cluster around the center with few extreme values. This is our ground truth, right? This is the real world distribution we're trying to learn from. Now, here's a critical question. When we split our data into training and test sets, does the split method matter? Watch what happens if we split naively. Let's say we just take the left half for training and the right half for testing. Do you see the problem? The training set and test set now have different distributions. The training data is skewed to the left, the test data to the right. This is called covariance shift or distribution mismatch. If we train a model on the left side data, we're teaching it about a different world than the one we're testing it on. Right? It's like training for a marathon in the mountains and then running the actual race on a pitch. The test result won't reflect the model's true capabilities. So what's the solution? Randomness. Watch as we shuffle these points. By randomizing the order of our data before splitting, we break any systematic patterns in how the data was collected or organized. Now, when the split 80% for training, 20% for testing, something beautiful happens. Both sets maintain the same underlying distribution.